Hello, and I'm here with my youngest student to give a lecture on amplifier theory. So, let's see if we can teach her something. There used to be something called the vacuum tube that revolutionized the world. It was very similar to a light bulb, and it contained a series of electrodes, and then the transistor came around. In short, let me lay you down. The transistor superseded the vacuum tube. So you had a plate, a fine mesh, and this object which was heated via a filament. And what happened is the current that would flow in this direction classically was governed by this equation. The voltages are referenced to ground. It's the plate voltage, which would be here, the grid voltage here, and so basically there's a tug of war between the grid voltage and the plate voltage, and it controls the plate current. This value is mu, which was typically between 2, believe it or not, to about 200 max. Our plate was typically in the hundreds to the hundreds of kilo ohms. But a typical value for this would be 20. A typical value for RP would be 7,000. In the case of a 6J5. Now vacuum tubes became very, very complicated. They started adding more grids. They started adding plates that focus the electron beam. But for the sake of this video, let's just assume a simple triode, which is the simplest that can amplify, called a triode because it has 1, 2, 3 elements. 1, 2, 3. So, triode, its equation. Now typically this was at a low voltage, this was at a high voltage, which would be a plus, and this guy had a certain negative voltage with respect to this guy. And so really this should be an absolute value here and a minus there. Same thing, you turn off the current by a higher voltage in the grid, negative. You can increase the current by putting more positive voltage here. Exactly how this works will have to be mentioned at another time. In 1947, they figured out you could build a controlling tube called a transistor for transconductance resistor or transimpedance resistor using doped silicon, negative, positive, and negative. It really looks like this. Some people will show the base region like this. The base is exceedingly thin compared to the other two. The collector, similar to the tube, is at a plus potential. This is at a more low voltage. And this here, on the base, would be at a plus voltage, although not as large as this one. If there's no voltage here, then no current flows. If there is a voltage here, and therefore a current flowing, then the larger current flows. But the control equation is that the collector current, which runs from collector to emitter, is controlled by the base current here. And in practice, beta is between 25 and 400. So there's two main control devices that everyone in electrical engineering must appreciate, and I'll explain how this can be used in an amplifier later. But the current has to be flowing, so if you cut the lead here, or got rid of the voltage, nothing would flow and it would saturate. In the tube's case, it's very different. If you cut the grid off, a maximum current would flow, the electrons flowing this way, so the classical conventional current would be shown this way. And it takes a negative potential to stop or repel the electrons back towards the cathode, which is this lead here, and the grid is in the middle, then you have the plate. So a vacuum tube actually behaves very similar, behaves like a modern field effect transistor. A rough comparison, these guys are good at controlling currents, these guys are good at controlling voltages, very large voltages. Typically you'd have 100 volts or more here, 100 volts or more here would destroy him. But essentially this is the history of electrical engineering and a core topic in microelectronics. Now, I guess macroelectronics isn't a thing, so we don't cover tubes anymore, which I think is a shame. So I've explained the theory, the most fundamental equation, the two components, and now I'm going to explain what these look like. This is what a vacuum tube looks like close up. An octal base, the top cap that had a wire hooked up to it, the getter, which is this signing metal that gets rid of the oxides that form during its operation, and then electrodes inside. Here's a close view, although you can't quite see it. The thing that controls this charge is those two in the middle. That's the grid. The filament is in the very center, and the plate's the outer part. Very interesting device. This might actually be a pentode, which is more complicated, but this is a vacuum tube, the first electronic component. This is an early transistor. It's hard to see. This particular device, 3 leads, emitter base collector, a tab that allows you to align it, and the parts. This is a modern transistor, as you may see in the classroom. It has a flat tab in a semicircular region. And when you're looking at the flat tab, remember the phrase, eat big cookies. From left to right. Emitter, which is where my thumb is at, that lead. This one here is the base, and that one is the collector. Remembering this simple acronym will ensure that you connect your transistors and microcontrollers and microelectronics in the right direction. If you put them in the opposite direction, the transistor will be destroyed.